All right, so having this integral, our next step is to factor out the r. So we're going to have 4 integral 0 to pi over 2. So I have r squared in both these terms, but it's under a square root. So if I factor it out of both terms, it's going to factor out as just r. And then I'm going to have square root of 1 minus sine squared t. And then out here I have r cosine t. Now, what you see here, the 1 minus sine squared t, this is how the trigonometric substitution works. Why are we going to make this substitution x equals r sine t? Because I can't do anything with square root of r squared minus x squared. But if I could somehow change that into a trig function, there's an identity that will simplify, an identity in terms of a constant minus sine squared, because we could manipulate that into being 1 minus sine squared, and we know that 1 minus sine squared is cosine squared. So we can make that substitution next. So this equals 4 integral 0 to pi over 2 of r square root cosine squared t times r cosine t. In a way, you could say that really what we're doing is we're taking advantage of the fact that sine and cosine have this identity that allows a difference of squares, which I cannot take the square root of, to a single square, which I can take the square root of. And that's really the engine of trigonometric substitution. And we're going to see at least one more type of substitution that we can do. They all revolve around that same concept, that if I have sum or difference of squares, I have various trig functions that will allow that sum or difference of squares to turn into a single square, and that single square can then simplify, because I know what the square root of cosine squared is. It's just cosine. So now I have, and I can gather some of these things together, I guess. The r and the r, let's put them together and make r squared. Square root of cosine squared t is just cosine of t, and then I have cosine of t, dt. I'll lose my dt's on all these. And by the way, square root of x squared is really absolute value of x, but you can sort of verify pretty easily that for our particular problem, cosine of t is always positive. Now, the next thing we're going to do is say, look, r squared is a constant with respect to this derivative. So I can factor the r squared all the way out of the integral for r squared, integral 0 to pi over 2. And then cosine times cosine is just cosine squared t dt. And now I have this. All right, so I was able to change this original integral, which is intractable, into this different integral that represents the same area, but can immediately be done. Well, not immediately. How do I know integral of cosine squared? Well, remember when we did this last time? This is why we did it. We know what the integral of cosine squared is. So we can say that this area equals 4r squared times the evaluation of t over 2 plus sine of 2t over 4, and we're evaluating that from 0 to pi over 2. All right, so let me just copy that onto our next page. I'll continue and finish this up. So the area of the circle we now know is equal to 4r squared times the evaluation of t over 2 plus sine of 2t over 4, evaluated from 0 to pi over 2. So arguably, this is one of the reasons why these integrals of trig powers are important. So it allows you to handle things like this. He says while he's stalling to turn the page. All right, so now this equals 4r squared times, okay, so we're going to plug in the pi over 2. So let's put a little parentheses here, plug in the pi over 2 here, so I'm going to have pi over 4. And then I'm going to have sine of 2 pi over 2, that's sine of pi. Sine of pi is 0, so I have 0 over 4. And then when I do plug in my 0, my lower limit, this one's going to be 0. Sine of 0 is 0, so I just have 0 when I plug in the lower limit. And so this gives me 4r squared times pi over 4. And lo and behold, that is pi r squared. And that is how I know that the area of a circle is equal to pi r squared. Now, so the original proof of this circle pi r equals pi r squared predates calculus by centuries. So how it was originally done was using a limit of polygons. Some people consider it to be the first use of a limit in mathematics. It's probably something around 600 AD. I don't really know the dates for that. And then calculus is invented in like the 17th century. So calculus basically is confirming a result, but this is using techniques that you're familiar with. Like setting up an equation for the curve and doing area under the curve. So it's not geometric, it's analytic. And sort of a more modern way to show that the area of a circle is pi r squared. And now you know a convincing reason why this formula is true, instead of just because my math teacher told me so in 5th grade. All right. Next up, we want to apply this to some different kind of shapes.